Hello friends, in this video we are going to see what the program control operations are. We have various program control operations like jump and label, jump list, switch and return. Then we will improve the project which it was developed in the previous video. The first instruction is jump and label. We can use the jump instruction to interrupt the linear execution of the program and resume it from another network. Let's see how this instruction in this program is working. Here we have three networks. In the first network, a jump instruction is used, which refers to network 3. Now, this instruction is not activated, so the CPU runs all the networks from the first one to the last one. When the jump instruction is activated, which refers to network 3, the program execution jumps to network 3 and the second network won't be executed. Let's write a simple program to see how we can use these instructions. Here there are the program control operations. The jump instruction is already explained. The next instruction is jump negative. That's like the simple jump instruction, but it works when the RLO is 0. Let's use it. Here, the destination network must be identified by a label. We can use the label instruction to identify a destination network in which the program execution should resume after a jump instruction is executed. Now I can refer to label 1, which is placed in the third network. Let's insert some simple contacts and coils. Pay attention, we can just use one jump instruction in each network. Also, only one label can be used for each network. Note that the entire label names must be different. Now let's test this program. The jump negative instruction does its jump if the RLO is 0. Now the CPU is executing all the networks. As you can see, we can change the state of contact with Ctrl plus F2 and Ctrl plus F3 keys. Now let me change the state of this contact. It makes the RLO to be 0 behind the jump negative instruction. At this time, the program jumps to label 1 in the third network. So the second network won't be executed at all. Pay attention. The jump and label instructions must be in the same block, and it does not matter where the label is used. The jump direction can be towards a higher or lower network. Let's see the next instruction, jump list. This instruction defines several conditional jumps and continues the program execution in a specific network depending on the value of the K parameter. The destination network must be identified by a label. In this program, first we need to activate the start contact. Now the K parameter value is 0, so the program jumps to the destination network with label 0. If the K parameter value was 1 or 2, the program would jump to network with label 1 or 2. We can increase the number of destinations up to 32 places. Pay close attention. If the K parameter is greater than 31, for example 40, the program does not jump and the CPU executes the program from the next network. Let's see the next instruction, switch or jump distributor. This instruction defines multiple programs jumps to be executed depending on the result of one or more comparison instructions. We can select the data type of the instruction from here. Actually, this instruction is like the jump list. First, we need to activate it. Then the destination network will be determined based on some comparisons. Here we can select the comparators. For each condition, we must determine a label at the output part. If none of a condition becomes true, the program jumps to the last destination. For example, here the K parameter value is 0, which is less than 5. It satisfies the first condition, so the program will jump to the first destination with label 0. For this instruction, we can increase the number of outputs up to 32 when we are using the S7-1200 CPUs. The next instruction is return. This instruction can stop the execution of a program block. As you know, when a CPU is in a running mode, it reads and stores the state of all inputs, then executes its program from the first network to the last. Then it updates the state of all outputs. The CPUs repeat this cycle, which we call it the scan cycle. If a return instruction is used in the main block, a CPU does not execute the remainder of the network. Instead, it exits from the main block and repeats its scan cycle. If we use the return instruction in a function block or a function, the CPU will return to its previous block. Alright, we did a project related to this tank in the previous video. In this project, we are going to improve it further. I want to change the code such a way that if the liquid level is less than 10%, the fill light to start blinking. And if it is greater than 90%, the discharge light to start blinking. Alright, this is the previous project. As you can see, we had defined the two push button lights which were not used in the previous videos. Also, these tags were defined for the lights in the TIA. Here we have the liquid level at the output of the displayer function based on percent in QD18. At this network, I am going to insert some conditions. So let me insert a switch instruction. When the QD18 or liquid level is less than 10%, the program will jump to a specified network. I use the blinker fill light label for that. Also, if the liquid level is greater than 90, the flow of the program will jump to another network with the blinker discharge light label. Alright, at this network of the blinker fill light label, how can we get the fill light to blink? We can do it by using the timers to blink this output, but here is a simpler way to do it. Let me open the device configuration. Select the PLC, then at the bottom select the system and clock memory item. Now let's click here to define a memory address as a clock memory byte. For this PLC, we can select the byte number from 0 to 4095. Let me choose the last byte, so every bit of the M4095 address will blink with a specified frequency. For example, the last bit of the M4095 will be on-off with a frequency of 0.5 Hz. Now let me use this bit to turn on-off the fill light. After this line, I don't want to execute the next condition, so I use the return instruction to restart this program from the first network. Here I need to define a bit of memory. I haven't used the M1.0 address, so I write it here. Similarly, let me insert a suitable program for the discharge light, but with another frequency. Now what about if the two conditions are not satisfied? For this case, here I can refer to the first network. Now let's test this program. As you can see, when the liquid level is less than 10%, the fill light starts blinking. Now let me press the fill push button to start the filling process. When the liquid level is greater than 10, this light will be off. As you can see, when the liquid level reaches 90%, the discharge light starts blinking. Alright, I have improved this program during the 3 lessons. Now let's transfer that to the PLC and retest it. Well, when I press this push button, the PLC starts the filling process. When the water level rises above 10% and error occurs in the PLC operation, which has not been seen in the previous test with the TIA simulator. Let me show you what this error is. In the program here, when the water level reaches 10%, the CPU jumps to the first network. Then the program is executed. Again, at this network, the CPU jumps to the first network. So this cycle will be repeated, and the CPU won't exit from the program to update the PLC input-outputs. To solve this error, I should use this label at the end of the program. Also, this network should not be empty. So let's write a simple program here, something like this. Now, if I transfer this program to the PLC, we will see that the PLC will execute the program without any error. Pay attention. If you want to be a good PLC programmer, you need to write your programs, test them, and try to find and resolve the problems. Then transfer your programs to your PLC and retest them over and over to come up with an errorless solution. Now let's see word operations which are AND, OR, XOR, INV or invert, decode, encode, select, multiplex, and demultiplex. You may have studied these operations in a microcontroller course already. Let's see how we can use these operations. Well, let's review the simple AND operation. In ladder language, we can have the AND logic with the series contacts. On the right side, we can see the AND logic operation in the FPD language. For this logic, we know the output is true if both the inputs are true. Well, we can have the AND logic for 8, 16 or 32 bits at the same time. This is the ladder symbol of the AND instruction. In this case, we must select the data type which can be a byte, word, and double word. This instruction links the value at input IN1 to the value at input IN2 bit by bit using the AND logic and queries the result at the output. Let's see what this instruction does. The first input is F0. We can convert a hexadecimal number to its binary format. This is the second input. As you can see, if we want to enter a binary number, we should use 2 plus sharp before that. And if we want to enter a number in hexadecimal form, we should use 16 plus sharp. Alright, this instruction does the AND logic bit by bit. As you can see, none of the two similar bits in both inputs are true at the same time. And we know if we perform the AND logic bit by bit, the result is 0. So when this instruction is activated in this example, the result is 0 for all bits. The next instruction is OR logic. For the OR logic, we know the output is 0 if only both inputs are 0. In other words, the output is true if any of the inputs is true. Also, we can have the OR logic for byte, word, and double word addresses. This instruction links the value at input IN1 to the value at input IN2 bit by bit by OR logic. Let's take the same example for this logic. In this case, the output is true if any bit of the input is true. So the result will be 1 for all of the 8 bits. So we will see the FF number in hexadecimal form at the output. The next operation is XOR. This instruction links the value at input IN1 to the value at input IN2 bit by bit by XOR logic. For this logic, the output will be true if only one of two inputs is true. So if we use this logic bit by bit, we can get the result. Where this binary number is equivalent to 3C in hexadecimal form. Let's test this logic in TIA. Here are word logic operations. Let me insert an XOR logic. First, we need to select the data type for its input-output. Then we should assign an address to each input and output. Now let's start the simulation. Alright, we need to change the inputs to the desired value. So I right click on each input and select the modify operand item. In this window, first I determine the format and then enter a desired value. Using the same way, you can test the other word logic operations. The next instruction is invert. It is very simple like the previous instructions. Here we must choose its input data type. This instruction inverts the signal status of the bits at its input. As you can see, if we convert all 1 to 0 and all zeros to 1, we will reach F0, which is the invert of 0F in hexadecimal form. Let's see the next instruction, decode. This instruction just accepts a positive integer number and its output data types can be a byte, word, or double word. This instruction is used to set a bit in the output value that is specified by the input value. For example, here the output value is this number. If we activate this instruction, it sets bit 4 of the output address and resets the other bits. Pay attention, bit numbers start from 0. So here this bit will be 1 and the other bits will be 0. The equivalent hexadecimal number of this result is 10, which will be sent to the output. The next instruction is encode. This instruction reads the bit number of the least significant bit in the input value and sends it to the output. For example, here the bit number 3 is the first bit, which is a 1. So this instruction gives us a 3 at its output. The select is the next instruction. Here I choose the short integer format for its output. This format only needs a byte of memory. If we activate the select instruction, depending on its G input, this instruction selects one of its inputs, IN0 or IN1, and copies its content to its output. Here on the left side, the G input value is false or 0. So the first input number 10 will be copied to the output. If the G input value is true, then the second number 20 will be copied to the output. The next instruction is multiplex. If we activate this instruction, it copies the content of the selected input to its output. Actually, it's like the select operation, but here the desired input is selected by a number at its k parameter. Here its value is 0, so the first value IN0, which is 10, is copied to the output. If the k parameter is 1, the next input will be copied. For the S7-1200 CPUs, we can have up to 32 inputs, and then we can select one of them. Here, if the k parameter is not equal to 0, 1 or 2, the last input will be sent to the output. Now let's see the last instruction in this video, the multiplex. When we use this instruction, it copies the content of the input into a selected output. Here the K input is 0, so the number 25 is copied to the first output. If it is a 1, the number 25 is sent to the next output. Otherwise, this number is copied to the last output. Similarly, we can have up to 32 outputs for S7-1200 CPUs. Let's do a simple project. Suppose there are 8 entering gates and each gate has an optical sensor. Let's write a program in which each optical sensor can open its gate, and also an operator can open and close all the gates manually. Well, let's define the input-output tags. First, I need two push buttons to open and close gates. We have 8 sensors that are connected to the PLC inputs via the byte number 1. I don't need to write all tags. Let's click here and drag it to insert the other tags automatically. Also, we have 8 gate doors that are connected to the PLC outputs. Alright, first I need to modify my hardware configuration because I need 10 digital inputs, but the CPU supports 8 inputs. So click on the device configuration. Now I am going to use another digital input module besides the CPU. Alright, we can see the PLC output tags, but what about the sensor tags? Pay attention to the address of this input module, that it starts from i8.0, but we have used byte 1 for the sensors inside the tag table. So I must modify the address of the PLC tags inside the tag table or change the addresses of this module. Okay, the input and sensor addresses of the new module inside the tags table are matched together. Now you can see the defined tags for the sensors on the new module. Now let's start the programming step. We can use each sensor to open its related gate, but here is a simpler way. I can use a move instruction to open the 8 gate doors based on the 8 optical sensors. Also, the operator can use the open push button, so I need to use the OR logic with this number to open all doors. Also, I can use the AND logic to close all gates manually. Now let's test this program using the sim table. We have learned to use this table before. These are my defined tags. As you can see, each sensor can open its gate. If I press the open push button, all gates will be open. And if I press the close push button, all gates will be closed. Now we are going to study shift and rotate operations. Here we have basically two types of the shift and rotate instructions. Shift right and left, rotate right and left. And finally we will do a simple project together. Let's see the first instruction, the shift right. We can use the shift right instruction to shift the content of an operand at the input bit by bit to the right side and query the result at the output. This is its ladder symbol. First, we need to choose our data type. Here the input value is F0 in hexadecimal form. We use the N parameter to specify the number of bits position in which the specified value should be shifted. This is a binary number that is equivalent to F0 in hexadecimal. Here, each bit will be shifted 2 bits to right. Note that with this instruction, we lose the right bits. Also, this instruction adds 0 on the left side to fill the empty bits. So for this example, the result will be 3C. Let's see another example using the help window. Pay attention if the selected data type uses the last bit to store the sign of a number such as in an integer format. This instruction uses the sign bit to fill the empty bits on the left side. As you see, we lose the bits which are on the right side. The shift left instruction is like the shift right, but it shifts the bits to the left side and adds 0 to fill the empty bits. Let's see them in TIA. Here is the shift and rotate instruction list. Let me use a shift right instruction. Here I use a contact to enable the instruction. Well, I need to use a positive signal edge detection. Pay attention, in this program the input and output addresses are the same. Let's test this program. Well, let me modify the input value. As you know, each hexadecimal number is equivalent to 4 bits. So, to see the result of the shift right instruction, I have used the number 4 at the second input. Every time I activate this instruction, the CPU shifts 4 bits to the right side and inserts 0 to the left side of the MD2 address. If I repeat the shifting action, the output will be 0 after 8 times. Pay attention, if we don't use the positive signal edge detection, when I activate this instruction for 1 second, the CPU will execute the program rapidly about 1,000 times, so I will just see 0 at the outputs. The next instructions are rotate right and rotate left. We can use the rotate right instruction to rotate the content of the operand at their input bit by bit to the right and query the result at the output. This instruction is like the shift right, but here we don't lose the right bits because the bits will be used to fill the empty bits on the left side. The result of this rotation for 2 bits is this binary number, which is equal to E6 in hexadecimal format. Now try to rewrite the previous program with the rotate right instruction. In this program, let me define and use the clock memory, which I explained about it in the previous video. Now, let's transfer the program to the virtual PLC. Let me modify the input value. As you can see, the input value is being rotated with 0.5 Hz every 2 seconds. Also, we can use the watch table to see the rotation in a binary form. Alright, let me insert the used memory address and select the binary format for that. Now you can see the bits are rotating. Okay, let's do a simple project. I want to write a program to use an air blower to sort taller boxes in the following plant. I mean, if there is a box with this pattern on the conveyor, we must use the air blower to change it. Here we have 2 start and stop push buttons, the air blower and a motor which are connected to the PLC outputs with 3 sensors. The sensor A detects the taller boxes. Sensor B detects all of the boxes which are on the conveyor. And finally, an encoder is connected to the conveyor. The encoder sends regular pulses when the conveyor is running. So if the sensor B detects a box on the conveyor, we can use pulses from the encoder and the shift instruction to have the box position. Let me explain the program. Then you may want to improve it further. I use a double word memory MD2 to store the box position on the conveyor. If a box is passed from sensor B, it gives us a negative pulse. Then this OR instruction inserts a 1 on the right side of the selected address MD2. At the next network, with each pulse from the encoder, this bit that is shifted to the left side, it shows us the position of the box. For example, if a box reaches the air blower, this bit will be 1. Alright, I need another double word memory to store the position of the taller boxes using the same program. The sensor A detects these boxes. In the next network, I used an SR instruction to stop the motor. Then I used the encoder pulses to shift the 2 previous memories, MD2 and MD6. In the third network, I have used an AND logic. Here, if a box is reached to the air blower and also if it is a taller box, then the output will be equal to this number. Then, based on this comparator, the air blower will be on for 1 second. Alright, this is the program. Pay attention to test this program. I have used the clock memory to generate pulses instead of using an encoder at the PLC input. We know each pulse coming from the encoder means a little movement of the boxes. Now let me test this program using the sim table. Notice that I can turn the conveyor motor on, off using the start and stop push buttons. When both the sensor A and B generate a negative pulse, it means a taller box is placed on the conveyor, which is moving to the left side. Note that when a taller box reaches the air blower, it is turned on for 1 second. Try to write and test this program to understand its logic. Thanks for watching this video. See you in the next one.